he has gone, become the director, but it's a smaller place, so easier to control, and hopefully, but every institution has its own problems.
No, but Brother Pradeep, every place has its own complexities, small, big, whatever it is.
It's true.
Yeah.
I think we are there, or what?
Yeah.
4. Okay, only 9:04. We have time. Yeah. Huh? I will also make you co-host, Tatsuya, just in case you see somebody unmuted.
Yeah, that is a problem, yes.
Yesterday it was very good. We had 80 people all through, so it was very good.
The sequence is same, right?
Yeah, sequence is the same. Just that we were planning to start at 9 o'clock.
Okay.
But then I realized that you were not there, and also a couple of others who did not get the message. So again, we decided to start it at 9:10.
No, no issue. Because I'm not staying on campus, it takes few minutes for me to. I moved to closer place, but still.
Acha. Your wife and daughters are here?
No, they're still in Pune. I'm alone. You are on the INST board, right? I think you are the chair.
Yeah. Yesterday, all the presentations were of very high quality.
Okay. Yeah, at least I thought I will be able to join in the afternoon, but last minute, something has not been done, so I had to oversee again, continue the meeting. So.
Sure.
And morning we had all the DST directors some other meeting chaired by Professor Balram, so I had to be there.
Oh. What is Balram doing?
They have now started this one, no, that National Science and Technology, something university.
Oh.
He's the chair of the committee, that is. So he wanted us to kind of give our ideas.
What time was it?
Sorry?
What time was it?
Whole morning, it almost started at 10 and then ended at 1.
Okay, I think we should, we are at 9:09 now.
Can I start?
Yeah.
Okay, let's start. Good morning to everyone, or good afternoon to everyone. Okay, I'm Tatsutsuka from Tokyo University, and I'm so happy to chair the first session. The first speaker today is Professor Pradeep, our great host. Maybe I have nothing to say about him, and I found that there is hours from Japan in the list, Nikkei Asia Award. So I want to share this copy. Nikkei is one of the most famous newspaper company, and he was awarded about activity for purification of water by using nanotechnology. And this is a copy of the newspaper. And I was asked to make a comment on this activity, and I made some comment around here. And I said that this activity was motivated by a human lab or sense of duty by Professor Pradeep. So I was very much impressed with his activity, not only science. Okay, let's welcome Professor Pradeep. But before starting, let me say this. So you have 25 minutes. Every speakers have 25 minutes and 5 minutes for discussion. So I will make a call at 22. So 3 minutes before the end of your talk. Okay, so please cooperate to run the meeting as scheduled. Okay, let's welcome Professor Pradeep.
Thank you. It's always a pleasure to talk about one's science, especially in this meeting. Thank you, Professor Tatsuya Tsukura, for that introduction. I have been to Japan some 25 times or so, so it's always, Japan is dear to me. I thought in this meeting, we are affirming and reaffirming that nanoparticles are molecules. And clusters are molecules, and nanoparticles also tend to be molecules. I would like to take this further and make some additional, some recent and some old observations. And in the spirit of the GRC style of meetings, I will also show you some unpublished work. So we know that this area is evolving, and that's Tatsuya talked about, very many people are getting into it. That is reflected in the citations. All that is good, and lots of people have worked or walked before us, and we are standing on the shoulders of many people. So we are aware of these. But when we start looking at a title such as nanoparticles or molecules, molecules are their properties. So take, for example, water. Look at the whole gamut of properties water has. And many of them are chemical properties, physical properties, bulk, water bulk, and water in the solid state. And no canvas is enough to fill all those properties, but there are too many of them. But have we touched that the scale of properties of molecular systems as far as clusters are concerned? No, we have a molecular formula. We have a molecular weight, as we all know, for most of the molecules that we have. Very well-defined compositions can be understood from isotopes. And we have molecular structure. Beautiful molecular structures, largely because of the geometric and electronic shells. We know this. Tsukuda talked about the various kinds of superatomic configurations. We have very many of these structures. Gold 25, silver 25, silver 44 and 102 and several others. But then there are plenty of gaps. We don't know enough about these molecular properties. If you start filling a table of these, we don't have enough. Now, this can be as simple as something like, in order to observe these particles, it is probably not so easy. If you put them under a TEM, they aggregate. I can't see these. But very recently, Anantu has been in a position to create conditions under which TEM images of cluster crystals are possible. So this is silver 29 crystal. And you can see it under TEM, and you see the lattice of the clusters, cluster lattice you are seeing. And you look at this in great detail, you see all those lattice fringes corresponding to the cubic structures. You see 110, 200, 111, 110, all of those you can see in great detail. So structure is by and large okay, and even very early signs are there that traditional methodologies like TEM, we can go and observe these. But how about other molecular aspects such as molecular reactivity? So this is something that we pursued in great detail. How about looking at reactions of clusters, reactions between clusters? We are not talking about reactions on clusters as catalysis would suggest. Something that we looked at some time ago was this reaction between this and that. As if, can you write a chemical equation of this kind, A plus B giving you C plus D? Now what we did that time was we took this fluorothiophene, this ligand, and Au25 and Ag44 protected with the same ligand, mixed these two together. And you did a matrix-assisted laser desorption ionization mass spectrometry. And if you do that for Au25, you get only this peak and that peak. These are the only peaks that you are supposed to be seeing. But just because of this mixing, you see something new and something new here. And this is the atom exchange that Tsukuda was also talking about in the beginning. You wait a little bit, and this peak goes down, and the intensity distribution is different. And you go further, you will see that the distribution is completely different. This is altogether gone. Kindly mute all of you so that this can be audible better. So how do you do this chemical reaction? Let's say you start asking this question: when one atom is exchanging, which atom is exchanging? So gold-25 has the central atom and the icosahedral 12 atoms and the staple 12 atoms. And Ag44 has 4 distinct kinds of atoms: the icosahedral atoms, dodecahedral vertex, and dodecahedral facial, and the staple atoms. So you ask, if one atom comes from here and goes into here, where will it go? Or one atom from here goes into here, where will it go? And how will this evolve in the course of time? Obviously, at that point in time, the only tool we had was computation. So you ask this question, is it governed by energy? Take, for example, Ag44 and put gold into it. Well, gold is more noble than silver. So any position, whether it is I or DCV or DCF or S, all of these positions are giving you negative energy, meaning that gold going into silver cluster is energetically feasible. How about the reverse? If you ask this question, let us say if I were to take silver into gold 25, all of these positions are positive just because silver is, in this particular case, silver is not favored into gold lattice. But if you do a chemical reaction between Au25 and Ag44, you can create this. Simultaneously, you create this. And so you ask this question, if I substituted the C position for Au25, simultaneously, if I change the I position of 44, the energy is negative. But if I do this, keep the C the same, but put the atom here in the DCV position or DCF or S position, the energy is positive. If you do this kind of analysis, you see that the I and I substitution, I here and I here, the energy is more negative. So thermodynamic reasons suggest that there are preferential occupancies in position, and you can go ahead and compute this further and greater and more substitutions. But more and more substitutions you do, there are more and more positions, more and more isomeric possibilities, and much more complexities come in. All of these can be considered. Well, chemical reaction doesn't mean that you can just do that. You can do this particular chemical reaction. And when you do that chemical reaction, you find that this is what you have to begin with. And this is also what you have to begin with. Although this is an equimolar mixture, this intensity is lower than this because this ionization is less efficient. So I have labeled it as 0.25 to indicate that there is no silver in it. 25.0 to indicate that there is no gold in it. And if you mix this together, you get these peaks as we just talked about. But in addition, you see something. If I expand this region, I get this. And well, you can say that this exchange chemistry is probably more facile. And there may be a in this thermodynamics that I told you earlier, that is only enthalpy, but there can be entropic contribution. And that entropic contribution would suggest that this is more facile because there is more entropy in this particular system. And it is minus T delta S in the delta G. So therefore, that contributes to greater free energy stabilization for the system. Well, one can go on, but at the same time, there is a possibility that this can be a dimer of this and that with 2- charge state. So can you go and see these? So we probed this in the initial stage of this reaction, even before those exchange products are appearing, you see a peak here, and that is a 2- species. And you see the mass separation is 0.5. And that, if you wait a little further, just after 2 minutes, you start seeing these features. Now, right now, what you're seeing is not matrix-assisted laser desorption ionization. You see electrospray. So therefore, the time required for preparation and analysis is faster. So you can do in a few tenths of seconds, you can do this analysis. So how is this happening? This is happening because clusters could be coming together, and you can compute what would be the kind of structures. And in these kinds of structures, you see that interatomic distances in clusters can be as short as this, leading to atom exchange. Now, this is not the only thing that you can do. You can certainly look at a number of other possibilities. So you start from silver 25 and add a little bit of gold to it. And then keep on going. Well, this reaches an equilibrium. You add more gold to it, more gold 25, I mean. And you can take this composition all the way here. Not artificial transmutation. Gold 25 is not becoming silver 25, or silver 25 is not becoming gold 25. But it is possible that every atom can be exchanged. There are other products for the mass balance. So how do you comprehend this? Which atom is moving and which chemical bond is breaking, etc. That would require a nomenclature. just as an organic chemist's nomenclature would imply which chemical bonds the electron has to transfer, which bond to break, which to assemble. All of these would imply a nomenclature. So we wanted to build a nomenclature, and for that we took this structure. So if you look at the structure in greater detail of gold-25, you see there is a ring there. And there is another ring actually, this is perpendicular to this. There is another ring coming towards you. This is not quite clear in this particular projection. If you rotate this a little bit, you can see there is one ring that is going there, another ring that is going there, another ring that is there. And that gave us an idea to build a structure. So here are those rings, red, blue, and green rings around the icosahedron. So we took the central atom here, and you can see these 12 atoms we are representing in this kind of a fashion. If I were to take the I atom at there and take 1 and 2, these 1 and 2 atoms are 1 and 2 here is connected with a ring. This is connected with a ring, and that ring is in this particular case sulfur gold sulfur ring. This we call the D1 ring. Opposite to that, there is 3 and 4 atoms. It is connected with another ring. 5 and 6 connected with another ring. 7 and 8 connected with another ring. And 9 and 10 connected with another ring. And 9 and 10 connected with another ring. 11 and 12 connected with another ring. So this is apparently the kind of structure that you have. If you have such a structure, you imply that certain chemical bonds are tied together. For example, this chemical bond is tied together with a ring. That means that these chemical bonds should be shorter. And in fact, the structure gives you that kind of an idea. But even more important aspect is that this structure is one in which you're having a unique kind of bonding. You look at this structure, it represented in a very well-known structure. This well-known structure is called the Boromian Ring. So if I were to assume that the center there is an icosahedron, and the ring that I'm talking about are these 3 rings, this is a Boromian ring structure composed of 3 rings. So what is so unique about this? One chemical bond, if I were to break this, let us say this ring will come apart, and that means this will come apart, this will come apart. And so any chemical bond you can break, and the entire structure can be broken. Similarly, it can be reassembled. That means it is extremely fast to do this kind of structures, and we propose these names as aspicule structures, implying that aspis is shield, and cules come from molecules. Aspicule implies shielded molecules. Now, this kind of a nomenclature also allows you to write the structure. For example, in this particular whole 25 molecule, you have, let us say, D13 and D23 staples. Let me say, go back and say D13 position and D23 position are occupied by, let us say, instead of phenylethane thiol, some other thiol. Then I have a structure, but instead of D13, if I say D33 position is occupied, this can be a trans structure, this can be a cis structure. So all of these nomenclature related attributes can come into the name, and we can draw it on a blackboard, for example. So this is not gold-25 alone. This can be 102 or several other structures. You can also build optical activity and all of those into these structures. Now, the point is that such chemical reactions, I can see which chemical bond is breaking, how are they reassembling. All of these come from this nomenclature, which also implies that clusters can exhibit dimers. So we showed that cluster dimers are indeed forming in the mass spectrometer, not only in chemical reactions. Such reactions imply that you can have molecular reactivity leading to precision alloys. Completely new alloys can be made. For example, we made a gold iridium alloy by reacting gold-25 with iridium clusters. Synthetically, it is possible to build 2 clusters and connect them together and create such structures and make specific chemical bonds. And this is indeed feasible also. Unfortunately, we could not crystallize it, but we computed the optical absorption spectrum, and that matches very well with the theory. So interparticle reactions is a way forward or a very important direction implying molecular reactivity. So earlier thing that I told you is that a gold cluster and a silver cluster come together, and then they form, the reactions happen because of a dimer. But this is, we said that from this dimer, every other species is coming. But this is not the only thing. You have this particular dimer, but there can be many other dimers. So imagine the first few minutes of the chemical reaction, you have this dimer. But then a little later on, you see other kinds of dimers happening. For example, let us say AU-AG24. This can dimerize with AU25, or it can dimerize with AG-AU24. All of these species make these chemical reactions very complicated. And in the course of time, we see many dimers evolving. And finally, these, let us say 54 minutes into the chemical reaction, we see dimers between these. See, this is a dimer, 23, 27, 25, 25. All of these are M50 structure. Nuclearity is 50 atoms, but there are very many combinations that come about. Now, we study this in great detail to understand that these chemical reactions, what are these structures? What are these compositions? We look at that by collision-induced dissociation. I am not getting into more details of this, but just to tell you that silver 25 decreases in the course of reaction, but then AG24AU comes up and it decreases in the course of the reaction. And as this decreases, AG23AU2 comes in. And as this decreases, AG21AU4 comes in. So you can see a whole set of consecutive chemical reactions. And finally, an equilibrium is getting there. And that is the M25 nuclearity of the alloy that you are seeing. So all of these are beautifully evolving in this system, a very complex chemical equation and chemical dynamics. So is it, when that chemical reaction is happening between A and B cluster, it is also possible that within one given cluster, atoms are colliding or clusters are colliding and atoms could be exchanging. So this is called cluster dynamics, similar to water. When water molecules come together, atoms can exchange, hydrogen atoms exchange. Can you see these? And if you see these, you can say that they are indeed molecules, just similar to water. So for that, we did this experiment called isotopic exchange reaction between nanoparticles. So in this particular case, we made silver 25 with 107 isotope of silver and silver 25 with 109 isotope of silver, pure isotope. Well, 97, 98% isotopic purity. So in this particular case, the peak is at 5142. In this particular case, it is at 5192. So these are pure compounds, and that is the pure compound, and this is the pure compound, and these are represented like this. But the moment you mix these two together, we were so surprised, and of course, this is what we were expecting, that complete isotopic exchange happened, and this is completely gone, and this is completely gone, and with the aspicule nomenclature and the structure, if you recall, this reaction should be very fast. So in fact, we could measure the first spectrum at 15 seconds. Just after mixing, it takes a little bit of time to connect the second to the mass spectrometer. The second one is 20 seconds, 25 seconds, 30 seconds. All these features are gone. So that means that there is an extremely fast atom isotopic exchange. Well, it is almost similar to that of water. But how do you study the dynamics? Well, when you
3 minutes. 3 minutes.
So when you say that such a chemical reaction occurs, you have the kinetics associated with it. So here is, you can study this particular reaction, 29 reaction, which is slower, and you can monitor it over time window of, let us say, 500 minutes or something, you see a tri-exponential decay corresponding to 3 rate constants. One is the surface, we attribute them to the surface exchange and the slow exchange within the clusters, and then an equilibrium. And you get numbers which can be calculated as well. Of course, reactions, there is no end to it. You can do intercluster reactions leading to the kind of things like trimetallic or tetrametallic clusters. So you can build that story to something to the extent of penta or hexa kind of alloy clusters, ultimately leading to high entropy alloy clusters. It is also possible that clusters can react and give you completely new clusters. So here what we showed was the reaction between Ag12 and Ag18. These clusters give you 2 other clusters, 16 and 17. We crystallize them. It is also possible that this cluster and that cluster, just like 2 molecules, they can co-crystallize and they can separate, reassemble. All of these become possible also. Clusters also can react with nanoparticles. So here is a polydispersed nanoparticles of silver. You mix it with gold 25. Well, what you get in just a few minutes, a completely monodispersed alloy nanoparticle system. Now, you follow the course of the reaction. This is also chemical reaction between nanoparticles and clusters. Now we study this with several polydispersed systems. A highly monodispersed system will do this chemical reaction very fast. Highly polydispersed will do that a little slower. And we get crystals and things like that. And I have to conclude this now. This is not the only thing that we can do. Molecules will do supramolecular chemistry. So clusters will form supramolecular structures, and such supramolecular structures such as Ag29 will give you a supramolecular adduct with cyclodextrin, and there can be 6 cyclodextrin adducts. And some of these adducts, for example, if I were to put a cyclodextrin here and here, this can be trans or cis. So there can be isomers in such systems, and we can isolate these isomers. We can create assemblies, and we can assemble these for this kind of plasmonic nanoparticles or gold nanorods. And what this means is that molecular chemistry or molecular organization or molecular materials of this kind will produce a completely new array of systems. Going from the periodic table of Tsukuda, you can go to a new kind of material systems with such clusters. Let me conclude by saying that I started out asking that molecules and their properties. On the one side, we have all of these water kind of systems. Today, we have molecular formula for clusters, a molecular weight, a molecular structure, molecular absorption emission, molecular reactions, molecular assembly, molecular co-crystals. But look at the kind of gaps. We don't know enough about the phase transitions, energies, physical properties, mechanical properties. We are beginning to explore this. Electrochemical properties. What is that future like? Obviously, with the 100 and odd clusters of this kind, that space of molecular properties will be so vast. The science was done by my students at IIT Madras with lots of collaborators, including some of you who are in the audience. Thank you very much.
Thank you very much for the profound and insightful talk about the molecular nature of the clusters. We still have several questions from the audience, so let's go one by one. So can you please directly ask Pradeep about the question? First one is Vivek.
Yes, good morning, Professor Pradeep. As usual, very exciting talk. And it's amazing to see the nanoclusters acting like a molecule. My question is about your dimer chemistry. So I'm just confused that why they form AG-AU heterodimer rather than AG-AG or AU-AU. If I just look at the surfaces, an AG surface will have a better weighting factor with AG and AU with AU. But somehow you're forming the heterodimer. So what could be the driving force?
So it is this, Vivek, this is not the only dimer that is there. As I told you in the later this year's Jack's paper, all kinds of dimers form. This particular dimer that I just mentioned, I suppose you are seeing this. If you are not seeing, I'm sorry about that, because of some.
No, we're not seeing your screen now.
Yeah, you will be seeing it now. So it is not that we have just this cluster, a dimer. There are all kinds of dimers possible. This is what we originally thought would be present. And later on, I was telling you that there are all kinds of dimers that you can get. So this dimer is what we thought originally, resulting in all of these alloys. But there is this AG1 AU24 and AU1 AG24 that can also dimerize. And in fact, all of these dimer populations we see. In fact, these major peaks are alloys, and the minor peaks are dimers.
Okay.
And those dimers, their populations keep increasing. Here is a dimer. Here is a dimer. All these are there even at the very end of the chemical